All right. So we're going to be doing start Unit 8. We're going to be covering 8.1 to 8.3. Really, though, on this 8.1 is just like kind of a refresher of what is an acid and a base. 8.2 is pH. Finding pH, negative log of the hydronium ion concentration, right? So those are going to be really, really quickly gone over. But 8.3 has to do with strong acids versus weak acids, strong bases versus weak bases, and knowing or realizing how a weak acid or base will set up an equilibrium where that does not happen with a strong acid or base. So when you have an acid-base chemistry or a reaction, one way you can represent it is like this, where A, they usually write the acid as HA, and you're going to dissolve it in water. Now, what is A? A is whatever anion, right, is bonded to the hydrogen. So, HNO3, right, then the ion would be NO3. In HCl, the ion would be chloride ion. You get it? So H bonded to some anion, right? And what does that do? Well, it reacts with water. You can kind of see that, there you get the transfer of your hydrogen. This is written as a Bronsted-Lowry, right? Or you could also, though, see that it's a Arrhenius acid. Remember that? Because it is ionizing in aqueous solution to form hydronium ion, right? So that would be this would be an Arrhenius. Or if the H went to the H2O, that would be the accepting of a hydrogen, the donating of a hydrogen by HA. That makes it the acid. Remember that? So anyway, bottom line, you get hydronium, and then you get the free anion. We've learned this before back in Unit 4 because all we talked about were strong acids and bases, but strong acids and bases fully react, fully dissolve, fully dissociate, whatever you want to say. Those are all, in this case, kind of synonymous. Because it is disassociating, because the anion is going free, the hydrogen is going free, hydrogen ion is going free, but it's attaching to the water, right? So that could be dissociating, you could call it dissolving, you could call it reacting, because it is a reaction, right? The H gets transferred to H2O. With strong acids and bases, we've talked about this before, it is basically a completion reaction. And I kind of wrote it down here. Here we have a double arrow up here, but you can see I kind of wrote it over here. Remember what we were kind of saying? Well, it turns out that remember how most reactions are at least a little bit reversible, right? So I drew a tiny, tiny little reverse arrow there, right? But in a sense, this has a large K value, a large KEQ, but when the species is an acid, we call it Ka. Just like we called it, Kc or Kp. When you write the equilibrium constant for an acid, it's called Ka. And for strong acids and bases, the Ka is greater than 1, and very often much greater than 1. For some of these acids, the K value is 1,000,000, right? 10 to the 6th. Okay? Remember these, somewhere on a handout I gave you in Unit 4, we said that there were 6 strong acids, and you need to kind of remember which ones are strong. Oops, I spelled that wrong. The 6 strong acids are HCl, HBr, HI, HNO3, HCl of R, and H2SO4. There's a 7th acid that has a Ka around a little over 1, so it does have a K greater than 1, but it's not as huge as the Kas for the other ones. So chloric acid, which is HClO3, sometimes is included in strong because it does have a Ka greater than 1, but it's not nearly as high as the Kas for all those other guys. Okay, so bottom line is the ones you see in maroon font up there, those are definitely the 6 strong that everyone agrees upon. And every once in a while, people include chloric acid. Okay? So now we're going to contrast that strong acid with a weak acid, which does not fully dissociate, does not fully react. It sets up a reversible reaction in water, with water, that has a small KEQ value, and again, we would call it a Ka, And for these weak acids, Ka is less than 1, right? So the reactant side would be favored. The undissolved, there's more undissolved or unreacted acid in the beaker. We're going to draw the particle diagram over here in a second where I have the beaker drawn. Then there is dissolved or reacted acid, all right? And again, many of these have a Ka much less than 1, 10 to the negative 6, 10 to the negative 7, 10 to the negative 8, 10 to the negative 5th, stuff like that, okay, Kas. Again, as I mentioned, unreacted / undissolved HA remains at equilibrium. So let's kind of draw that up in the beaker. What does that kind of look like then? If you had to draw a diagram. So we're just going to use HA, or we could use HF. Let's use HF. So I put some HF into water, and it's going to set up an equilibrium, right? It's going to be, it's going to be HF plus H2O, and then you're going to get H3O plus, and you're going to get F minus, right? And we know that's going to be an equilibrium because HF is one of the many, 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 many weak acids. I only wrote 4 of them over there on the left, but there's hundreds. If you're not one of the 6 strong ones or 7 strong ones, you're weak, okay? So what would this look like? Well, some of it is going to react, so you might have a little bit of H3O plus and F minus, but most of it remains bonded together, right? Okay, and the amount of the ratio of what remains undissolved versus what's dissolved is going to have to do with the value of Ka, right? Whatever the value of the equilibrium constant is. Okay, but that would be what it would look like. Well, why does it dissolve? Well, guess what? HF is, even though it's covalently bonded, it's polar, and it dissolves as a polar covalently bonded thing, yes? But once in a while, if you remember, we kind of talked about this, what happens, like when this happens is, how does water remove that hydrogen ion? Well, if you remember, we did something like this, and then remember how this oxygen then approaches that hydrogen. Remember we've drawn that up, and it pulls that hydrogen off and makes H3O, yes? So it is a reaction, okay? And so this reaction, though, doesn't happen that much, as much in the forward direction at equilibrium as, the reverse. So the rates of formation and unformation are equal, but the concentration of hydronium will be much less than the concentration of HA. So if you were asked to write the reaction for the dissolution of nitrous acid HNO2 with water, or the reaction of HNO2 with water, again, these weak acids, you write them like a Bronsted-Lowry, okay? This is how we would write it. And so with a Bronsted-Lowry, the acid is a proton donor. So then on the product side, you're going to get H3O, yes? And then you're going to get whatever anion this is, which is NO2, okay? And it's a 1 minus because it's bonded to 1 hydrogen, right? Okay, and so then you would say, okay, well, Bronsted-Lowry wise, in the forward direction, right, this is the Bronsted-Lowry acid because it's donating the hydrogen. This is the Bronsted-Lowry base. Are you with me? Okay. But then, okay, and then this is your HA, this is your water, this is your H3O, and here's your A minus. You would want to make sure that you put aqueous there and there. But how about the reverse? If you recall, what we had said was, with Bronsted-Lowry, with these guys, and we didn't know about equilibrium then, but I said, these guys are always reversible. These reactions can go in the opposite direction. And so what about the opposite direction? Who would be the acid and who would be the base? And what are the conjugate acids and bases? We're going to need to know those when we talk about acid-base equilibrium. Okay? So if you recall, in the reverse direction, what would happen? What has to happen to go from H3O to H2O? the H3O has to donate the hydrogen, remember? So then this becomes the acid in the reverse direction, right, in the reverse reaction, and this becomes the base, yes? All right, because it's accepting it in order to become that. What are the conjugates? These guys are the conjugates. Because remember, a conjugate is just a hydrogen difference on either side of this equation, right? So it's, or you could say, you know, this is a Bronsted-Lowry acid. This is the conjugate base, right? If this was the Bronsted-Lowry base in the reverse direction, then the species that differs by a hydrogen, HNO2, is its conjugate acid. Okay? So that's like the conjugate acid base pair, and this would be the base, and this would be its conjugate acid if you look at the forward direction, yes? Or this would be the acid, and this would be its conjugate base if you're going in the reverse direction. Okay? So why don't you guys try the next one real quick, and I'll write it in. Okay, so yeah, so you have acetic acid. The hydrogen from the acetic acid is going to go to water to make H3O, and you're going to be left with the acetate ion. Okay, so this is the direction of the hydrogen. In the reverse direction, right? This is what would happen to recreate the product side. So this would be the acid. This would be its conjugate base. On the reactant side, this is the base. This would be its conjugate acid, because in the reverse direction, hydronium acts like an acid, right? And acetate ion acts like a base. Now, once you have these reactions, though, you can write the equilibrium expressions for them, and we're going to call it Ka if it's an acid. We would call it Kb if it's a base. So what would the Ka be? Now, it would be concentration of hydronium, right, times the concentration of NO2 over the original concentration, well, you know, H of HNO2. Because those are all aqueous, and the water is a liquid, and so it doesn't appear. You with me? So H3O plus times, sometimes the acetate ion is shown as AC minus, so you don't have to write that whole thing, over, and then you could say like HAC, where the AC is acetate, or you could write the whole thing C2H3O2. Got it? So this is the form that the equilibrium constants are going to take. And if you think about it, it's like it's H3O in general, right? Sorry, concentrations, times A minus, right? Remember, like your free anion over HA. You see that? So like the general form of the Ka is going to be, you know, the hydronium times whatever the anion is, right? Looking at these, right? Hydronium, right, times the anion, the second one, hydronium times the anion in the numerator, and the HA, either HNO2 or HAC, in the denominator. So that's the general form that these equilibrium constants are going to take.
Is the AC there's acetate?
That's acetate. Yes, it's an abbreviation for acetate. Sometimes you'll see that HAC. It's not HA. The AC is for acetate. Okay? Okay, so to quickly review calculating the pH and pOH, but this is again only for strong acids and bases. In fact, what we're going to learn in 8.3 is when you have a weak acid and base, how can you figure out the pH? Okay? Besides measuring it, right? Is there a way to calculate what you think the pH will be? And the answer, of course, is yes. So, in this equation here, you might want to say, okay, well, what would be the pH of a 0.2025 molar HI solution? Well, HI is one of the strong acids. So you know that if this solution starts out at 0.025 molar, 100% of this is going to dissolve. Notice that it's written as a completion reaction. So the concentration of hydronium, which is really what's acting as the acid, right, is 0.025. Yes? Remember this from Unit 4? So the pH is going to be the negative log of 0.025. Okay? And then we'll get that number, or I should have had that number. It might still be on my calculator. Yes, 1.60. Remember about the sig figs? This is a concentration. It has 2 sig figs. But in a logarithm, only the numbers past the decimal point count in the sig fig count, right? The one before it doesn't really count. You know, well, it's there, but it's not part of the significant figures because this number has to do with the power of 10. Remember that? Okay, anyway, so what would the POH be? Well, 14 minus, right? 1.60, right? Or 12.40. Remember that? The pH plus POH equals 14. So the concentration was given as 0.0030 molar. So 0.0030 molar. We know because this is a strong base, it is going to fully ionize into that much hydroxide. So when you take the negative log here to find the P, you're going to be finding the POH first, right? It's going to be the negative log, right, of 0.0030, right? And the negative log of that is 2.52. Okay. What would the pH be? Well, 14 minus that. Minus 2.52, which is 11.48. So the pH of that concentration of a sodium hydroxide solution is going to be in the basic range, and that's how you do it. Remember that? All right, so let's talk about this thing called estimating the pH of an acid. So the way you would do this is, if you recall, remember that you're taking a negative log, and somehow the power of 10 that goes along with that concentration, right, has something to do with that number before the decimal point in the pH. I know you guys know that, right? So this in this case, this exponent here, right? Whoops, I didn't mean to erase it. Come back to me. I'm not sure why it won't. So yeah, that exponent has something to do with the number before the decimal point in the pH. So anyway, how would you estimate a pH? So if you think about this number right here, 2.5 times 10 to the negative second, is between 1 times 10 to the negative first and 1 times 10 to the negative second, right? It's bigger than 1 times 10 to the negative second, but smaller than 1 times 10 to the negative 10, right? Okay, and so since that value is in there, the logarithm is going to be in between 1, right, the negative logarithm, and 2, right? Right? And so isn't the pH of that going to be 1.x, whatever the x is, based on this exact number here? Okay? So the way you would do this is to estimate a pH, you write your concentration in a scientific notation. You take the exponent number, like 2 in this case, like the negative log, 2, and then you subtract 1 from it, and that's what goes before the decimal point. And then the x is essentially the logarithm part, right, of the 2.5. Got it? So that would be 1.x. In other words, it's this concentration, 2.5 times 10 to the negative second, will give you a pH between 1 and 2, and that's what that 1.x is designating. Again, I'm showing you this because sometimes you see this as a notation, right? Well, how about to estimate the pH of a base? You do the same as above, but the estimate is going to be the POH, and you subtract from 14, right? So for this case, let's estimate the 0.0030 molar hydroxide ion concentration. Well, that's 3 times 10 to the negative third. So you take 3, you subtract 1 from it, and that becomes the number before the decimal, and then you put an x, right? So because this is somewhere between 1 times 10 to the negative second and 1 times 10 to the negative third. It's in here somewhere, right? So this number, the pH of this, is going to be somewhere between the pH of 2 and the pH of 3. See? And so it's going to be 2.x. So sorry, POH. So the POH is going to be 2.x. So 14 minus 2.x will be 11.x. All right, so you should be able to estimate a pH of a strong acid or base from this concentration. Okay, or if you know the concentration, even if it's a weak base or weak acid, if you know that this is the actual concentration of hydroxide or hydronium, you can do this estimation. So again, kind of going back to 8.1 to 8.3, weak bases. So we talked about a weak acid. So a weak Arrhenius base. Now remember, the Arrhenius base, remember the Arrhenius definition, ionizes in aqueous solution to produce hydroxide ion, yes? And so you can see that bases like KOH, CuOH, or ZnOH2, those will liberate hydroxide ion when you dissolve them. So this type of weak base is an Arrhenius base. And if you remember back to Unit 4, we said there are only a small number of strong bases. The group 1 hydroxides, and then calcium, strontium, and barium hydroxide, which we know have an equilibrium constant, but they produce so much hydroxide ion they're considered strong. Because why is this? Because remember, the hydroxide ion is largely, quote, insoluble, right? In the chart, in the solubility chart. Remember, now we know that it doesn't mean completely insoluble. We know that that insoluble on the chart means slightly soluble, right? So, bottom line is, if you dissolve potassium hydroxide in water, 100% of the KOH dissolves into OH minus and K plus. Whereas if you dissolve copper 1 hydroxide or zinc hydroxide or iron 2 hydroxide or iron 3 hydroxide in water, it's not going to be a 1-to-1 ratio. This is not going to fully dissolve. And so we write it with a double arrow, and these reactions would have an equilibrium constant, and they would be called Kb. Okay, it's a KEQ, but it's specifically called a Kb. Okay, and so how would that look? Well, it would be this concentration times this concentration over that concentration. You guys got that, right? Okay, just like any other equilibrium constant that has a double arrow. The other way you can be a weak base is to be a Bronsted-Lowry base. Now it's stated in the notes down below, most of these Bronsted-Lowry weak bases are going to contain nitrogen and bonded to something. Because if you recall that nitrogen has this unshared pair that with water, right, can come up to water and kind of pull that hydrogen off, right? It's in a Bronsted-Lowry type reaction. So most of the weak Bronsted-Lowry bases contain a nitrogen with an unshared pair like that. So these weak bases participate in a proton transfer reaction. Sometimes they are protonated. That is, they accept a hydrogen. So when an NH3 ammonia, reacts with water, it doesn't have any hydroxide ion in it, so it can't be an Arrhenius base. Remember that, right? So we talked about that in Unit 4. This is a Bronsted-Lowry base, but it acts like a base and makes NH4, which now can act as an acid. It is the conjugate acid to the Bronsted-Lowry base NH3, right? NH3 is a base because it accepted a hydrogen. But in the reverse reaction, the NH4 is giving away a hydrogen to hydroxide to remake water, so it would be an acid, and it is the conjugate of this because it differs by a hydrogen. We got all that, okay? Now, so that's the example of the Bronsted-Lowry base. It does end up making hydroxide ion, but in this reaction, but remember what it doesn't do is it doesn't have hydroxide in its formula, so it can't ionize to make hydroxide ion. That's the Arrhenius definition. Now in general, how would you write this? Well, you have some base, and you're going to add water. The water will add a hydrogen to the base, and the way you write that formula is BH+. So whatever this was, like NH, so for NH3, you write N, you'd add a hydrogen, and then you put a plus, okay? And then hydroxide. how would you write the Kb? Well, this is you know, the concentration of BH plus times the concentration of hydroxide in the numerator. In the denominator, it would be the concentration of the base from the reactant side, and that would be the Kb. So as I said, these often contain nitrogen, and in a minute I'm going to hand out a table of some Kas and Kbs, which are a reference table, and you'll see that a bunch of these are in the middle. A bunch of these nitrogen-containing weak bases are in the middle of the handout. But so you have ammonia. Another one is called methylamine. So this is a formula. And so if you had to take methylamine and react it with water, how would you write it? There's another one, dimethylamine. That would be written C2, H6, and H or whatever. And then here, this one's one that has a kind of a benzene ring. It's called pyridine. But let's write the reaction products of one of these more complicated ones, not just NH3. Well, remember, so this is B, aqueous, this is H, so this is going to be BH. So you're going to write CH3, and then you put the H on the nitrogen, so NH3, and then it's plus. Okay, so in other words, remember how we said, like, where is the hydrogen going to go? Well, that hydrogen is going to attach to the nitrogen, right? Like there. The hydrogen from the water, right, is going to attach to there. So you'd write CH3, NH3 plus, so that's your BH, that's your base with the H attached and a positive sign, and then plus OH minus, and again, that's because the hydrogen went from there to there, but it attaches to the nitrogen, so you kind of show it attached to the nitrogen. You guys got that? Okay? All right. So again, since a weak acid or base does not go to completion, we're going to have to use equilibrium methods to find the hydronium ion concentration or hydroxide ion concentration at equilibrium, and that's coming up next when we talk about calculations involving weak acid base. So whenever you say acid base equilibria, you're pretty much automatically talking about weak acids or weak bases, because strong acids and bases don't set up an equilibrium, right? Okay. So let's look at this equilibrium expression. We can use hydrogen, a hydrofluoric acid as an example. All right, so of course that's your reaction. How would you write the Ka? Well, I have it written in there, right? It's going to be hydronium times fluoride ion concentration over the concentration of the undissolved hydrogen fluoride. And you can look up this Ka. And what I would say, gentlemen, is on this table, if you look at the front and back, just like with the KSP of calcium hydroxide, there's some discrepancies in the Ks. Always look on the front side first, because it has some acids and some bases. But if you don't see the acid you're looking for, so not the acid you're looking for, right? Then flip it over and use the one on the back. Okay, so this on the back is only acids, but it's got many more acids. So on the front, the Ka for this reaction is 6.3 times 10 to the negative 4. Okay? So that tells you can actually see, right, with this KEQ less than 1, that the reactant side is predominating a lot, right? It's predominating a lot. Okay? The other thing that we're going to learn, and this is more important when we talk about titrations, is that it is possible to take the negative log of the Ka, not just the negative log of the concentration, right? You can take the negative log of anything, and if you take the negative log of the Ka value, you get what's called the pKa. And so you might say, what is it? Something like, yes, here's the Ka of hydrogen or hydrofluoric acid. What is the pKa? You're just taking the negative log. And the negative log of that is 3.20. Right? It's 10 to the negative 4th, so it's going to be 3.x, isn't it? Right? Okay. Now, looking at the Ka can tell you the relative strengths of weak acids. So the value of Ka, right, can help you like say, okay, all these acids are weak acids, but which one is the strongest of the weak, right? Well, the one that makes the most H3O, huh? And that's going to be the one that makes the most product, and the one that makes the most product is going to be the one with the largest Ka, correct? See? So if you're given a list of acids and you're asked which acid is the quote strongest, now these aren't strong, these are all weak acids, but which one is going to produce the most hydronium, it will be that one. Or you could compare pKa's, in which case, though, the lower the pKa, the stronger the weak acid. Okay? Remember, this Ka is just an equilibrium constant. Which one of these is going to make the most product, the most acid, right? It's going to be the one with the largest Ka, or, again, the smallest pKa. Because remember, smallest pKa means this power of 10 is smaller, huh? And it means it's a greater number. That negative power is smaller. And so which solution would have the greatest pH? Or the lowest pH? Well, the one with the larger Ka is going to produce the more hydronium. The higher the hydronium, the lower the pH, remember? Right? So you might be asked, which one of these two solutions, equimolar, you have to be doing equimolar solutions, in this case, well, those are the Kas. This Ka is larger than this. This is going to produce more hydronium, mole for mole, right? Mole for mole, this guy is going to dissolve more into hydronium than acetic acid, and it'll make more hydronium, and then that will give you a higher pH, or lower pH, I'm sorry, higher concentration of hydronium, but that means lower pH.